Hey everyone, my name is Sandip and today we will be solving LeetCode problem 3777. Minimum deletions to make alternating substring. Let's look at the problem statement. We are given a string S of length n consisting only of the characters A and B, and we are also given a 2D integer array queries of length q where query of I is one of the following. It's either a type 1 query or a type 2 query. Type 1 query says you're also given an index j. Flip the character at index j, that is A becomes B or B becomes A. So you just need to flip the character. Next, let's look at the type 2 query. So type 2 query has L comma R. Okay. Compute minimum number of character deletions to make the substring L to R alternating. Okay. So for type 2 query, we have given a substring L comma R and we need to find minimum number of deletions to make that string alternating. So what is an alternating substring? A substring is alternating if no two adjacent characters are equal. So it's like either A, B, dot, 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 or it's like B, A. So these are alternating substrings. Okay. Now we have to find minimum deletions to make that string alternating. Okay. Now return an integer array answer where answer of I is the result of ith query of type 2. So whenever we get a type 2 query, we have to store that answer in an array and finally return that entire array. Let's see an example for further classification. So we are given this string S as ABA and these are the queries 21211 and 202. Let's look at the first query 21, 2. It's a type 2 query. So we need to find number of deletions for the substring 1, 2. So if this is the string and this is the indexes, so substring of 1, 2 is this range. So this is the substring B, A. So this is already an alternating substring. We do not need to delete anything here, right? So the first output is 0. Next is a type 1 query where we go to index j equals 1 and we flip that character. So what do? We simply go to this index 1 and we flip the character. So we make B as A. So this is also done. Next we have a type 2 query from 0 to 2. Again compute minimum number of character deletions to make substring 0 to 2 alternating. So we have this entire substring and we have to make this alternating. So how many deletions do we make? We can simply delete this character and this character. So the final string is this, and this is an alternating substring. A substring of length 1 is also alternating, right? So how many deletions we made? We made 2 deletions. So 0, 2 is the answer for this particular example. The constraints are length of the string can be 2 to the power 5 and S of I, as I said, it only contains character A or character B, and number of queries up to 10 to the power 5. Examples like this, you can check the problem link in the video description, or if you want to take some time to think of the solution by yourself, pause the video here, else let's move ahead. Okay, so let's just solve for the smaller problem instead of solving the larger problem. So let's solve for this, where if we are just given a string, what is the minimum number of deletions to make it alternating? Okay, so mathematically we define a string S of length n as alternating if S of I is not equal to S of I plus 1 for all I greater than equal to 0 and less than n. So this is the definition for a alternating string. Now what is the only criteria that violates this condition, which is basically if S of I is equal to S of I plus 1. If we have such a pair, we call it a bad pair, and this will violate the condition of alternating string, right? So if we have such a pair, we have to perform some operation on the string such that the string becomes alternating, right? So what are the operations that we can perform? Either we delete this left character, or we delete the right character, or we delete the both. But we need to find minimum, right? So let's just stick to deleting either one of these and we will see if this works or not. Okay, so we have taken the sample string A, B, B, A. So let's find out the bad pairs. So first of all, A and B are different characters, which is fine. This pair is fine. Next, this index 1, index 2. This is both the characters are same. So this is a bad pair, right? Next pair is index 2 and index 3. Both the characters are same, B and B. So this is again a bad pair. So we have 2 bad pairs already. And then B and A, both are different characters. So this pair is fine. So we have 2 bad pairs here. So if we just delete the left characters from these pairs, what do we get? And this is alternating. So we deleted this and we deleted this. So we deleted 2 characters and we got an alternating string. Also, if you observe closely, we simply transformed this entire run into a single char and we got an alternating string, right? What do I call it a run? Run is basically a substring with the same number of characters. So this was a run of length 3 and we reduced it to 1 character and we got the alternating string. So number of deletions that we made was exactly run length minus 1. So length was 3, we made 2 deletions, right? So let's take a run length and see if it works for the same. So we have this string A here, and let's see, number of bad pairs is, this is a bad pair, again this is a bad pair, index 1, index 2, again index 2 index 2 is also a bad pair. So we have 3 bad pairs here. So if we just delete all the left chars from these bad, what are we left with? we're just left with a single char. We delete this and delete this, right? So essentially we transformed this entire single run into a single char, and the number of deletions performed was 3, right? Which is nothing but equal to the length of the run minus 1. So length of the run was 4 minus 1 is 3, okay? So if you think of it like this, then the number of deletions is nothing but the same as the number of bad pairs. So we have 3 deletions because we have 3 bad pairs here. Similarly here we had 2 deletions because we had 2 bad pairs. So minimum deletions is nothing but count of bad pairs, because if you see, what we are essentially doing is we are just transforming this entire run into a single character. And how many bad pairs do we have? Is 2, which is same as the number of deletions that we make, and which is the same here, right? So summarizing, if we look at single run of identical characters like A, to make it alternating, we keep at most one character. We just keep at most one character like here from this entire run, and so we must delete the rest. So we must delete the remaining characters. So that exactly costs run length minus 1 deletions, okay, which is exactly the number of equal adjacent pairs inside the run. Yeah, did you understand this? So length minus 1 is exactly the number of bad pairs that we have, okay. So we never delete across run boundaries. So once each run is reduced to one character, so once each run is reduced to one character, the neighboring pairs are automatically different. The neighboring pairs in this case are automatically different, right? So we never delete across boundaries. So we now know the minimum deletion is nothing but the count of bad pairs. So now let's try to use this intuition to solve for the larger problem. Okay, so now we add the type 2 query to list of criteria. So now we just have this type 2 query where it's written 2, L, R. So we need to find for this particular substring L, R how many deletions that we perform, and it has to be minimum, okay. So if we just have this condition, what we can do is we can just find the number of bad pairs in this particular range. That will give us the answer for this particular type of query, right? So if we just have A, B, B, A, let's keep an array of bad pairs. So what we will have, A and B, we compare these two first. These are different, so it will have 0. Now we compare index 1 and index 2 pairs, so they are same, so it's a bad, we have kept 1. Again, if we compare these two, they are again same, so we have kept 1 because it's a bad pair. Again, if we compare these two, they are different, that means it's 0, it's a good pair, okay. So we have these bad pairs now, we have compared all the pairs. Now we keep a prefix sum of this entire bad array. So we have 0, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 0 is 2, right? So we keep this prefix sum. Now let's say we get a query saying 2, 0, 2, which is this particular range. So we just need to find number of bad pairs. So number of bad pairs is we have to compare this and this, right? That's it, right? This is already present in our prefix sum. So if we just do a prefix sum of this to this, then we get the answer. So we get prefix sum of r minus 1, prefix sum of r minus 1, because we have to find all the pairs before this, like till this in this range, right? For this range, we have to find all the pairs in this range, right? Minus prefix sum of, we have to remove all the pairs before it, so L minus 1. So this is L, this is R, so we have to find this particular thing. So we just do prefix sum of r minus 1 minus prefix sum of L minus 1. So this gives us the answer, and this is roughly O of 1. So this is how we can solve the problem if you only have type 2 queries. Now let's add type 1 query. So now we can also flip some characters. So we just go to index j and flip a character. So if you flip a character here, this array also changes, even the prefix sum will change. So now this will not help us. So this is the exact condition for which we have data structures like segment trees or Fenwick trees. Segment trees and Fenwick trees, they help us achieve such updates in O of log n. Similarly, we can do a range sum in O of log n. So if we use segment tree or if we use Fenwick tree, they have updates to nodes in which take O of log n time, and similarly they have range sum. They have range sum property which also take O of log n time. And this is the exact reason we use these data structures. So we will quickly use Fenwick trees in this problem, and we will solve the entire problem now. Okay, so here I have drawn a visual representation of Fenwick tree of size 8. Okay, any node I stores the sum of the range I minus least significant bit of I plus 1 till I. So LSB here is the least significant bit of I. Okay, so this is the range that it will save. So here in this case 8 node saves 1 to 8, sum of the entire range 1 to 8. Node 4 saves the entire sum 1 to 4. Node 6 stores the entire sum 5 to 6. 7 stores the entire node 7 to 7. So this is the range for which it will store the sum or whatever you want to save. Okay. Similarly, for node 5 it contains 5 to 5. Node 4 contains 1 to 4. 2 contains 1 to 2. Sum of the entire range 1 to 3 contains 3 to 3, and 1 contains 1 to 1. So this is how Fenwick tree behaves. Now let's say I want to add some value to a node I. So let's say I want to add some value to this node 1. I want to add plus 1. So what I will do is I will keep going upward by finding least significant bit and adding it to it. So I increment this part, increment this, increment this, increment this. So what will happen is automatically the larger range which has this index automatically get updated until I reach the largest node on the top. Okay. So this is how update works. Similarly for the sum, what I do is I keep chopping off the last significant bit till I encounter 0. So for example, if I want the range 7, what I do is 7 is like 1 1 1, right? So this is how 7 is, node 7. So for node 7, I already find the sum range from in the range 7 to 7. Then I chop off this bit. What I get is 6 1 1 0. 6 will already come the range 5 to 6, and then again chop off this bit. So what I get is 4. So I get 1 0 0. So 4 will contain the range 1 to 4. So I already got, and then I chop off this bit. So then I got 0. So if you see, 7 contains the range 7 to 7, 6 contains the range 5 to 6, 4 contains the range 1 to 4. So I already got the entire range from 1 to 7. Okay. So this is how. So using binary numbers, this convict tree very easily helps us to do both updates as well as sums. Now let's use this in our solution and quickly write it. Okay, so let's quickly look at the code. I have provided the entire code in a link which is there in the video description. You can check it out as well. So we have the class convict tree and the constructor which initializes the size of the entire tree as well as the array, which is the bit array. Okay. Next, we have the same add and sum functions I have described previously. Add function simply adds that value to the node and propagates it upwards in the tree. Sum function similarly chops off the bits and keeps adding it to the sum variable s and finally returns the sum of that particular range. Range sum is nothing but it's for our convenience, so it's sum of r minus sum of l minus 1. Okay. Now the function min deletions takes two parameters, string s and queries, and this has I have initialized n as the length of the string. I have a character array, and then finally initialize the convict tree with n minus 1. Okay. So I iterate over the entire string, and if I see a pair of characters match, then I simply increment the convict tree with 1 because that is a bad pair. For I have to count such bad pairs. Okay. Now I have a list of integers answer, and then I iterate over all the queries. If I have a query of type 2, I have to find the range sum for l comma r, right? So I just call this function with l comma r. That's it, right? So I get my answer directly. Next, what if I have a query of type 0? I need to update that index. So how do I update? So for a particular index I, so I have to first remove the previous contributions and then add the new contribution, right? Because this index getting flipped. So this index updates which all values. So I compare I and I plus 1 and would have also compared the previous index with it. So like I minus 1. So I would have done, if these two characters are same, then this would have contributed a bad pair. Similarly, these two are same, they were contributed a bad pair. If not same, then it would have been 0. So whatever. So what I have done is I have simply checked first removing contributions, first removing previous contributions, remove. So what I am doing is, if j is greater than 0 and array of j is equals array of j minus 1, if these two are same, then simply decrement the convict tree because this was a bad pair previously. So I should remove that from the convict tree, right? So I have done j minus 1 comma minus 1. So this is comma minus 1. Okay. Similarly, if these two characters are same, if j is less than n minus 1 and array of j equals array of j plus 1, convict tree dot add j comma I minus 1. For this index, decrement this friend because this is also a bad pair previously. Now I simply flip the pair, I flip the value in that index, array of j is it is a, then make it b or make it a. Now I again do the same thing. Now I add the contributions. Now I add the contribution, same thing. If these two are same, these two are a bad pair, so f of j minus 1 should be plus 1. Again, if these two elements make a bad pair, then again fe dot add j comma plus 1. So I increment those index. So that's how we solve the entire problem. The overall complexity is, so since for each query it takes us log n to update or log n to query, so the total complexity is q log n. This is total time complexity. Cool. Okay, so that was all for this video. If you have any doubts, feel free to ask in the comments, and if you like this video, feel free to give it a thumbs up, like, share and subscribe. Thank you.